Hello students, I hope you all are doing good. The topic that we are going to discuss today is current electricity NCERT section 3.10 to 3.11. Disclaimer. The images, text and other materials used in our presentations are for educational purposes only. We respect the intellectual property rights of the original creators and owners. If you are the owner and have any concerns or issues, please contact us at sathee@iitk.ac.in and we shall remove the content immediately. Please note that the parts of the content may have been generated using generative AI, which is experimental. Index. So the topics that we are going to cover today is NCERT section 3.10 cells EMF internal resistance. NCERT section 3.11 cells in series and in parallel. So what is the objective to learn cells EMF and internal resistance? So basically to understand cells EMF internal resistance and voltage relationships. So an electrochemical cell, or we can say galvanic cell, is an electrical device which converts chemical energy into electrical energy. Okay, so in chemistry you have been studied in detail that there is a electrochemical cell which converts the chemical energy due to spontaneous redox chemical reactions. Okay, it converts chemical reaction to or create chemical energy to electrical energy. Okay, its main job is to help maintain a steady flow of current in the circuit. So we use a battery or a cell to maintain a steady current in the circuit. So that cell is known as electrochemical cell, okay, which converts chemical energy into electric energy. So this is the diagram for electrochemical cell. There is a electrolyte filled and there are two electrodes dipped in this electrolyte solution, and a resistance R is connected across it, the two electrodes, and its symbol is given in the B part of the diagram. So figure 3.12 is a figure is sketch of an electrochemical cell with positive terminal P and negative terminal N. Okay, the electrode on which P is written is positive terminal and electrode on which N is written is negative terminal. A and B are the points in the electrolyte typically close to P and N. Okay, so A and B are the points that are close to P positive terminal and negative terminal respectively. Okay, and the B diagram, the B section of the diagram is showing the symbol for cell. Okay, one long line, one short line, and long line represents positive terminal and short line represents negative terminal. Okay, positive referring to positive P and negative referring to an electron. So this is the diagram, figure 3.12. It has two main parts, a positive electrode P and a negative electrode N. Okay, in diagram you can see one is positive electrode and it is written on this P, and the electrode on which written N is written is negative terminal, negative electrode. Both electrodes are immersed in an electrolytic solution. Okay, both the electrodes are dipped or immersed in electrolytic solution. What is electrolytic solution? Which allows the flow of charges through it, flow of current through it. Okay, electrolytic solution. So now this figure A, okay, we are concerned with this now. So figure 3.2 A section. These electrodes transfer electric charges with the electrolyte. Okay, so these electrodes are used to transfer electric charges. Okay, so they transfer electric charges with the electrolyte. Okay, you may have seen the chemical reactions also in the chemistry. We are not going to discuss the chemical reactions in detail, but you know how the electrochemical cell works. The electrodes share electric charges or ions with the electrolyte. Okay, and positive ions get accumulated on positive terminal, positive electrode, and negative ions get accumulated on or negative charges get accumulated on negative electrode, and due to which potential difference is created between its two electrodes. Okay, the voltage on each electrode is, okay, now we are concerned with the voltage on each electrode. So on positive electrode creates a positive voltage V plus. Okay, this is the voltage on positive electrode. It is noted by, so how it is denoted? V positive, positive in subscript, which is greater than 0. Okay, since it is positive, it is greater than 0 compared to point A in the electrolyte. Okay, so there is a point in the electrolyte, you can see in the diagram. So compared to that A point, this electrode P is at positive voltage V positive, which is greater than 0. Okay, negative electrode creates a negative voltage minus V negative. Okay, so minus V negative, and V negative is equal to or greater than 0. You can see V negative is equal to greater than 0. Okay, not minus V negative. Okay, so V negative is greater than equal to 0, but the potential or voltage of negative electrode is minus V negative, which is compared to point B in the electrolyte. Okay, compared to point B, you can see in the diagram, compared to point B in the electrolyte, the potential on negative electrode is minus V negative, where V negative, its magnitude is greater than or equal to 0. Okay, but with negative sign. So again, diagram. When no current flows or a cell is not being used, okay, there is no current flowing between the electrodes. Okay, when there is no current flowing between the electrodes, so which means cell is not being used. We are not drawing any current from the cell. We have not connected any component across the electrodes, and circuit is not closed. Okay, this is the condition of no current flows. Either circuit is not closed, key is open, either we have not connected any external device with these electrodes, or cell is not being used, means current is not being drawn from the cell. Means like you can bought a cell from the shop and you are not using it, so there is no current drawing, you are not drawing any current from it. Okay, you have not unpacked it yet, and haven't inserted this cell in remote or clock. Okay, so this cell is now in which condition? Cell is not being used, means no current is flowing and no current is being drawn from the cell. So when no current flows or a cell is not being used, the electrolyte maintains uniform and steady potential. Okay, potential difference remain steady and uniform in the electrolyte when there is no current being drawn from the cell. When cell is not being used, then the electrolyte maintains uniform and steady potential. Why steady and uniform potential? Due to positive voltage at positive electrode and negative voltage at negative electrode. So there is a potential difference created across the electrolyte. No chemical reaction are happening. Okay, at this condition, no chemical reaction are happening. When there is no current being drawn from the cell, no chemical reactions are happening, and also the electrolyte maintains uniform and steady potential. So in state of no current, okay, in state when there is no current, we are not drawing any current from the cell, and cell is not being used. The total potential difference between P and N is, so at that condition, at that state, what is the total potential difference? Potential difference between positive electrode and negative electrode, between P and N. What is it? Positive voltage minus negative voltage. Okay, so V positive minus V negative. Okay, that minus that is outside the bracket is for the formula. We are taking potential difference, so we have to subtract negative potential from positive potential. Okay, so we are subtracting, we are taking potential difference. So total potential difference between P and N is V positive minus V negative. Okay, so minus will become positive. So V positive plus V negative. This is the potential difference between positive electrode and negative electrode, or we can say P and N, where V positive is equal to positive voltage compared to point A, and V negative is minus V negative is negative voltage compared to point B. Okay. Now this is again the diagram. So we are going to use this diagram in the entire topic because the topic is based on this diagram also. This difference is called electromotive force. Okay, the difference in both difference of potentials or voltages of both these electrodes is known as electromotive force. And what is this electromotive force? When cell is not being used. Okay, the potential difference between the electrodes of the cell when cell is not being used, when no current is being drawn from the cell, is known as electromotive force. So this potential difference is known as electromotive force. At what condition? That cell is not being used. Okay, if cell is being used, then the potential difference across its ends is not equal to electromotive force. Okay, so EMF. Okay, we are going to use this word EMF in our upcoming chapters also. So you have to clear your concept related what is potential difference, what is electromotive force. Okay, so EMF is the potential difference, but when cell is not being used, when there is no current drawing from the cell. So the difference is called the electromotive force, EMF, of the cell, and it is denoted by epsilon. Okay, or small e is also used for EMF. Thus epsilon is equal to V positive plus V negative. That potential difference we have calculated in our previous equation, V positive plus V negative. Okay, so EMF is equal to that difference, and it is greater than 0. Mark it as 3.36 equation, where V positive is positive voltage compared to point A and V negative is negative voltage compared to point B. EMF is actually a potential difference. So from here we can say EMF is actually a potential difference. Okay, but at specific condition named historically. Why it is called force? Electromotive force. So it is named historically before proper understanding. Okay, so earlier it was considered that it is the force that is pushing the electrons from lower potential to higher potential. Okay, so by historically, that before proper understanding that it is not force, it is potential difference. So before understanding, its name was electromotive force. So name was not changed after knowing its actual reason or its actual function. Okay, so name is not being changed. So its name remained electromotive force, but it is not any force. It is potential difference. Okay. So with resistor R connected across the cell, okay, if we connect the resistor R, any resistor R across the cell between its two electrodes, then outside the cell current flows from positive to negative terminal. Okay, as we know that if we connect any external device with the cell, then current flows from positive to negative, which is conventional direction of current. So outside the cell current flows from positive to negative, and inside the cell current flows from negative to positive. Okay, so you can see in the diagram, so when we connected this R across the electrodes of the cell, so current is, what is the direction of current? From P to N. Okay, and we can see across the resistor there are 2 points, C and D. Okay, so current is flowing from C to D through resistor. So current flows from positive to negative outside the cell, means across the external resistor R outside the cell from point C to D. But inside the cell current is flowing from negative terminal to positive terminal. Okay, from N to P. So inside the cell, current flows from negative to positive terminal, from N to P through electrolyte. So again this figure, the electrolyte has internal resistance R, which is simply opposition offered to flow of ions through it. Okay, so electrolyte has internal resistance small r. So the charges are flowing through the electrolyte. Okay, so there will be some opposition also. There is no completely free movement of charges across the electrolyte. There is some opposition that will be offered to the flow of charges. That opposition is termed as internal resistance of electrolyte, which is denoted by small r, which is simply opposition offered to flow of ions through it. When there is no closed path for current to flow, R is infinite. Okay, if we take R as infinity, okay, when no current is flowing through it, then be taken as infinite. So no current is flowing through the resistor according to the relation I equal to V by R. If R is infinite, means current I is 0. Okay, so then no current is flowing. This is called open circuit. Okay, when no current is flowing through the circuit, that means that is called open circuit. If some amount of current is flowing through the circuit, then it is called closed circuit. Okay, so if there is no current flowing, I equal to 0, then it is called open circuit, where V is the potential difference between point P and N. Therefore, potential difference V between point P and N is given by V is equal to, now what is the potential difference between point P and A? Okay, so now point P and N. So potential difference between the two electrodes of the cell. So we are going to calculate it. V equal to the sum of three potential differences. What is it? Potential difference between point A, P and A. Okay, so what is the potential difference between point P and N? Is sum of potential difference between point P and A plus potential difference between point A and B plus potential difference between point B and N. Okay, so we have divided this whole potential difference, which is across electrode P and N, into three potential differences between 4 points. What are these 4 points? P, A, B, N. Okay, so potential difference V between point P and N is given by V equal to potential difference between point P and A, then plus potential difference between point A and B, plus potential difference between point B and N. Okay, so this potential difference is equal to EMF. Why? Because we have connected the infinite resistor, due to which no current is flowing through the circuit, means that is open circuit. If no current is flowing through a circuit, it means this is the definition of EMF, na? What is EMF? Is the potential difference between the electrodes when no current is being drawn from the cell. So if no current is being drawn from the cell, or cell is not being used, there is no current in the circuit because R is infinite. So this potential difference between the electrodes will be equal to EMF of the cell, E. Mark it as 3.37 equation. So figure 3.12, again, as we know, potential difference V between P and N is given by V equal to E. Okay, that we have just derived, that potential difference is equal to EMF when there is no current being drawn from the cell. This is 3.37 equation. Now, does EMF E is the potential difference? This is the definition of EMF. EMF E is the potential difference between the positive and negative electrodes in an open circuit. What is open circuit? That is when no current is flowing through the cell. Okay, when there is no current in the circuit, then the circuit is called open circuit. Okay, we have connected the resistor R, which is infinite. Okay, we have considered the condition that R is infinite. Then if R is infinite, then current will be zero in the circuit. So EMF is the potential difference between the positive and negative electrodes in an open circuit when no current is flowing through the cell. Okay. So for finite resistance R, now the second case, if the resistance R is finite, not infinite. Okay. So if the resistance R is finite, then potential difference V across the resistor R will be V equal to E minus IR. Okay, so for finite R, potential difference will be equal to V equal to E minus IR. Why IR? Why we are subtracting this IR? V is equal to E is when there is no current being drawn from the cell. Cell is not in use. Okay, now V equal to epsilon minus IR. What is this IR? So this IR is the potential drop across the internal resistance. Okay, so what is internal resistance? The opposition offered to the ions in the electrolyte. Okay, so this IR is the potential difference or potential drop across the two electrodes of the electrolyte in the cell, in the electrolyte, not in the external circuit. Okay, so IR is potential drop across the cell due to internal resistance R of the electrolyte. Okay, so this is the condition now. Now this potential difference V is less than the EMF. Okay, when cell is not in use, then this EMF will be equal to the potential difference. Now cell is in use, current is flowing through the cell. Okay, now this potential difference V, which is across the resistor R, is less than the EMF. Because current is being drawn, there is some potential drop. Okay, there is some potential drop across the cell, in between the cell, not in the outside circuit. So this EMF of the cell minus current flowing through the cell, which is I, or into small r, which is internal resistance of the electrolyte. So this IR will be V is equal to IR according to Ohm's law. Okay, so this I or small r is the potential drop across the cell. Okay, so why this negative sign is there? So negative sign in IR, E minus IR. Why this negative sign is there? Negative sign in IR reflects current flow from B to A in the electrolyte. Okay, in the outside circuit, current is flowing from positive terminal to negative terminal. Okay, but inside the cell, current is flowing through negative terminal to positive terminal, from point B to A. Okay, so the direction inside the cell, direction of current inside the cell is opposite to the direction of current outside the cell. So that's why we are taking minus sign, negative sign. So negative sign in IR reflects current flow from B to A in the electrolyte. Internal resistance can be neglected when EMF is much greater than IR. Okay, if the internal resistance of the electrolyte is so small and the potential difference across its end when there is no current in the circuit means EMF. Okay, so I am repeating the definition so that you can get the clear idea that what is potential difference, what is EMF. Okay, EMF is when there is no current in the circuit, or potential difference is when there is a current in the circuit. So this potential difference is given by equation 3.38, which is V equal to E, that is EMF, minus IR, that is potential drop across the cell, inside the cell. So internal resistance can be neglected when this EMF is much greater than IR. Okay, so this EMF will be greater than the potential drop across the cell. Okay, So if value of EMF is much greater than this potential drop, then internal resistance can be neglected. Okay, so V equal to IR we use for in many applications or numerical solving. We generally neglect the value of internal resistance. Okay, but if it is of significant value, we have to take it. Dry cells typically have higher internal resistance than electrolytic cells. Okay, so dry cells that are in wristwatches. Okay, small cells that are in wristwatches. Okay, so that dry cells have typically high internal resistance than electrolytic cells. Following Ohm's law, V equal to IR. Okay, now we are V equal to that 3.38 equation. That was V equal to epsilon minus I small r. Okay, now in the external resistance, what is the potential difference for external resistor? V equal to IR. So V equal to potential difference across the resistor of resistance R. So in external circuit, what is V? Potential difference, which is equal to current flowing through that resistor into the resistance of that resistor. So V equal to I capital R for external circuit. So put this value in the equation 3.38. What was 3.38 equation? V equal to epsilon minus I small r. Okay, so put this value of V, equation 3.39 in the 3.38 equation. So IR equal to epsilon minus I small r. So V equal to IR according to Ohm's law. So after solving this, we will get the value of, after solving the previous equation, we will get the value of capital I, which is equal to epsilon upon capital R plus small r. Capital R is the resistance of external resistor and small r is the resistance of internal resistance of the electrolyte, and epsilon is the EMF of the cell when there is no current drawn from the cell, when cell is not being used, and I is the current through it. When I is equal to, where I equal to current flowing through the resistor of resistance R, E is epsilon equal to EMF of the cell, and small r is the internal resistance of the cell. Maximum current occurs at R equal to 0. Okay, when R equal to 0, then maximum current is drawn from the cell. What is the maximum current? When capital R becomes 0 in equation 3.40. In equation 3.40, if capital R becomes 0, means there is no external resistance connected, only a simple wire is connected across the electrodes, then maximum current flows through the electrodes. That is I max equal to epsilon upon small r. Cells usually operate below this to prevent damage. Okay, usually cells operate below this I maximum. Okay, to prevent damage. This I maximum can be very large. So cells usually operate below this I maximum. That's why we are connecting the external resistance capital R to reduce the amount of current in the circuit. Okay, because I max can be harmful or dangerous to components. Okay, so cells usually operate below this to prevent the damage to the circuit or other components of the circuit. Okay, now next section 3.11, that is NCERT section 3.11, cells in series and in parallel. Like resistors, cells can be combined in electric circuits and replaced by an equivalent cell for calculating currents and voltages. Okay, in capacitors also we have discussed the combination of capacitors. Okay, and also there is a combination of resistors, but cells can also be combined like resistors or capacitors in electric circuits and replaced by an equivalent cell for calculating the currents and voltages. There are two ways to combine cells. Okay, there are two ways. First one is cells in series combination and second one is cells in parallel combination. Okay, there are two ways, like there are two ways for capacitors. capacitors in series, capacitor in parallel. There are two ways in resistors. Resistors in series combination, resistors in parallel combination. Similarly, there are two ways to combine cells. Cells in series combination and cells in parallel combination. Okay, this is the diagram for cells in series combination. Okay, so here you can see in the diagram, there is two cells that are connected of EMF epsilon 1 and EMF of second cell is epsilon 2. Their internal resistance are R1 and internal resistance of second cell is R2. First cell is connected between points A and B. Second cell is connected between point B and C. Okay, and this is the equivalent diagram, that is E equivalent R equivalent. Okay, so the combination of these two cells can be shown in the form of one cell, that is equivalent EMF and R equivalent between points A and C. So figure 3.13, two cells of EMF epsilon 1 and epsilon 2 in the series. R1, R2 are their internal resistances. For connections across A and C, the combination can be considered as one cell of EMF E equivalent and an internal resistance R equivalent. Okay, the combination of these two cells can be considered as one cell, which is of EMF E equivalent, epsilon equivalent, or internal resistance R equivalent. So when two cells are connected one after another, it is said to be in series combination. Okay, when they are connected back to back. Okay, one cell is connected directly to the another cell. Okay, one terminal of the cell is connected to another terminal directly without any internal connection. Okay, so when two cells are connected one after another, it is said to be in series combination, as we can see in the figure 3.13. Let VA, VB and VC be the potentials at point A, B and C respectively. Okay, so you can suppose that VA, VB and VC be the potentials at point A, B and C respectively. So again this diagram, then V equal to VA minus VB. Okay, so we can let V equal to VA minus VB. That is the potential difference between the positive and negative terminals of the first cell. Okay, for first cell in the diagram, that is having internal resistance R1 and EMF epsilon 1, that first cell that is connected between points A and B. So then you can suppose that V equal to VA minus VB is the potential difference between positive and negative terminals of the cell. We already found this in equation 3.38 before. Okay, in equation 3.38 we have found the what is the potential difference across the cell when there is current flowing through it. Okay, also in the diagram it is shown that current flowing through it, I current is flowing through both the cells. Okay, if current is flowing through the cells, okay, in the circuit, that means potential difference will be less than the EMF. So potential difference V is equal to epsilon minus IR, that we have also seen or found in the equation 3.38, where epsilon is equal to EMF of the cell. I is the current flowing through the circuit, that is also shown in the figure, and small r is the internal resistance of the cell. Hence potential difference between point A and B. Okay, between point A and B, potential difference can be represented by VAB, which is given by VAB, VA minus VB. Okay, potential difference across first cell, that is between points A and B. So VAB is represented by VA minus VB, which is, what is the potential difference across the cell when there is a current in the circuit? Epsilon 1 minus IR1. Mark it as equation 3.41. Similarly, for second cell which is connected between points B and C, so potential difference can be represented by VBC, VB minus VC, which is equal to epsilon 2 minus IR2. Mark it as equation 3.42. Hence, the potential difference between the terminals A and C of the combination is. Now, what is the total potential difference between the across the two cells, that is between points A and C, is calculated using VAC equal to VA minus VC. This is the potential difference across both the cells, which is potential difference across point A and point C. Okay, so this can be written as VAC equal to VA minus VB, which is the potential difference between point V A and B. Then VB minus VC, which is the potential difference between points B and C. So potential difference across point A and C can be written as VA minus VB plus VB minus VC. Okay, we can split the potential difference across 2 points. Okay, if we want to find the potential difference across point A and C. So VAC will be equal to epsilon 1 plus epsilon 2 minus I R1 plus R2. How this thing came? Mark it as equation 3.4 through 43. By using the equations that we have seen in our previous slide, that is VA minus VB equal to epsilon 1 minus IR1, which was equation 3.41, and another VB minus VC equal to epsilon 2 minus IR2, which was equation 3.42. Okay, using that equation and putting in the above equation, that is VAC equal to VA minus VB plus VB minus VC. So putting these values, the values of 3.14 equation and 3.42 equation, we will get the 3.43 equation, which is VAC equal to epsilon 1 plus epsilon 2 minus I R1 plus R2. This is the equation we have found. That is the potential difference across both the cells. If we are considering the combination of these two cells as one cell, so this is the potential difference across this combination of cells. So replace the combination by a single cell. Okay, now you can see in diagram also they have replaced the combination in the form of single cell of EMF equivalent epsilon equivalent upon, or what is the internal resistance, R equivalent. So replace the combination by a single cell between A and C of EMF equivalent and internal resistance R equivalent. We would have VAC equal to E equivalent minus IR equivalent. Okay, if we consider this as one cell, then according to the formula that we have done already, VAC will be equal to E equivalent minus IR equivalent. Okay, this is equation 3.44. Now comparing equation 3.44 with 3.43. So comparing the equation 3.43 and 3.44, we get E equivalent equal to epsilon 1 plus epsilon 2. Okay, so comparing this with equation 3.43, which was VAC equal to epsilon 1 plus epsilon 2 minus I R1 plus R2. Okay, so comparing that equation with 3.44, we will get E equivalent, epsilon equivalent equal to epsilon 1 plus epsilon 2. And R equivalent will be R1 plus R2. And mark this equation as 3.46. So VBC will be equal to VB minus VC, that is epsilon 2 minus IR2, which was equation 3.42. In figure 3.13, we had connected the negative electrode of the first to the positive electrode of the second. If we instead connect the two negatives, okay, in figure you can see that we have connected the negative terminal of first cell with the positive terminal of second cell. If we connect the two negatives together, okay, we reverse the direction of this cell, second cell. We connect the negative terminal of first cell with the negative terminal of second cell. Then what will happen? Okay, if instead we connect the two negatives, then equation according to equation 3.42, that is written equal to VB minus VC equal to epsilon 2 minus IR2. Then we would change VBC equal to minus epsilon 2. Why we are taking now minus sign? Because cell direction of the EMF is being reversed. Means negative terminal of first cell is connected to negative terminal of second cell. So direction of EMF of second cell is reversed. So we will take minus epsilon 2 now in the equation 3.42. So equation 3.42 would change to VBC equal to minus epsilon 2 minus IR2. And we will get E equivalent will be epsilon 1 minus epsilon 2. What was E equivalent actually? In equation 3.45, epsilon 1 plus epsilon 2. If cell is connected wrongly, means negative terminal of one cell is connected to negative terminal of another cell, then EMF will be epsilon 1 minus epsilon 2. If epsilon 1 is greater than epsilon 2. Okay, mark it as equation 3.47. The rule for series combination clearly can be extended to any number of cells. Okay, so we can extend this result to n number of cells. Okay, if the equivalent EMF of two cells is epsilon 1 plus epsilon 2, then equivalent EMF of n cells will be epsilon 1 plus epsilon 2, so on up to epsilon n. Okay, similar case for the equivalent internal resistance. Okay, so the equivalent EMF of the series combination of n cell is just the sum of their individual EMFs. Okay, so simple algebraic sum of their individual EMFs. And the equivalent internal resistance of a series combination of n cells is just the sum of their internal resistances. Okay, equivalent internal resistance is also simple algebraic sum of individual internal resistance of n cells. This is so when the current leaves each cell from the positive electrode. Okay, so this thing is applicable when current leaves each cell from the positive electrode. Means all the cells are connected in the right way. Means negative terminal of one cell is connected with positive terminal. Okay, so when current leaves from each cell, then this condition is valid. Then there is a simple sum of all the EMFs and simple sum of all the internal resistances to get the equivalent EMF and equivalent internal resistance. Okay, when all the cells are connected correctly. If the cell is connected incorrectly in the circuit, that is same terminals. If positive terminal of one cell is connected with positive terminal of another cell and negative terminal of cell is connected to negative terminal of another cell, then this connection is incorrect or opposite. Then EMF will get reverse sign. Okay, so if in the combination the current leaves any cell from the negative electrode, okay, if any cell is connected wrongly, that means current is leaving from negative electrode. The EMF of the cell enters expression for equivalent with the negative sign. Okay, so we will take the individual EMF we will take in the expression for equivalent will be of negative sign, like we have done. If we connect this second cell in opposite direction, then magnitude of E2 will be minus E2. Okay, or minus epsilon 2. If in the combination the current leaves any cell from the negative electrode, that is cell is connected wrongly or in the reverse direction other than other cells, okay, beside other cells, the EMF of the cell enters the expression for E equivalent with a negative sign. Okay, so in the expression of E equivalent we will take the individual EMF of that cell that is connected wrongly with negative sign. Okay, as in equation 3.47 that is mentioned, E equivalent is epsilon 1 minus epsilon 2. Okay, if we connect this epsilon 2 or the second cell in the opposite direction. So next is cells in parallel combination. Okay, we have done the series combination. Now we'll move to parallel combination. So next consider a parallel combination of cells like this diagram. Okay, This diagram is shown in the figure 3.14, two cells in parallel. For connection across A and C, the combination can be replaced by one cell of EMF E equivalent and internal resistance R equivalent, whose values are given in equation 3.54 and 3.55. Okay, we will going to derive the equation 3.54 and 3.55. So two cells are in parallel given in the diagram. For connection across A and C, the combination can be replaced by one cell of EMF E equivalent. Okay, like in the second part of the diagram. So equivalent diagram is combination of all the cells in parallel. So it can be shown in the form of one cell with EMF equal to epsilon equivalent and internal resistance is equal to R equivalent. Okay, next consider a parallel combination of cells, figure 3.14. I1 and I2 are the currents leaving the positive electrode of the cells. Okay, you can see in the diagram also. So I1 and I2 currents are leaving the positive electrodes of the cell. Okay, and entering the negative electrodes of the cell. At the point B1, I1 and I2 flows in, whereas the current I flows out. Okay, so I1 and I2 currents are combining at B1 point. Okay, and they are spreading at or separating at B2 point. Okay, I current is divided across two cells at B2 points, and this I1 plus I2 current is again combining at point B1. So at point B1, I1 and I2 flows in, whereas the current I flows out. Okay, so since as much charge flows in as out, so I equal to I1 plus I2. We can say I equal to I1, I2, because I1 and I2 combining and making I current. Or we can say I current is dividing into I1 plus I2. Okay, so mark it as equation 3.48. Now again diagram, and let VB1 and VB2 be the potentials at B1 and B2 respectively. Okay, so VB1 you can take the potential on B1 point and VB2 is the potential at point B2. Then considering the first cell, okay, considering the first cell having EMF epsilon 1 and internal resistance R1, first cell. Then considering the first cell, the potential difference across its terminals is VB1 minus VB2. Okay, so now potential difference we are calculating across the first cell, that is VB1 minus VB2. Hence from equation 3.38, this is the equation 3.38 again, V equal to epsilon minus IR, we can write V equal to VB1 minus VB2, that is equal to epsilon 1 minus I1 R1. Okay, now I is not same across the cells. So I1 R1. Mark it as equation 3.49. Points B1 and B2 are connected exactly similar to second cell. Okay. So points B1 and B2 are connected exactly similar to second cell. Here considering the second cell, we also have V equal to VB1 minus VB2. Okay, these both cells are connected across the same points B1 and B2. Okay, so potential difference across them will be VB1 minus VB2. Okay, equal to, now across second cell potential difference is epsilon 2 minus I2 R2. Put it as equation 3.50. Combining the last three equations. Okay, so combining the last three equations, we are coming to that result that I equal to I1 plus I2. So according to last equations, that is V equal to VB1 minus VB2 for first cell and V equal to VB1 minus VB2 for second cell. Okay, which is equal to, for first cell, which is equal to epsilon 1 minus I1 R1. For second cell it was V equal to epsilon 2 minus I2 R2. Okay, so reduce the value of, or derive the value of I1 and I2 from that two equations, and according to that equations and this equation I equal to I1 plus I2 that we seen in first at the beginning of the topic, cells in parallel combination. So put the values of I1 and I2 in this equation, which is epsilon 1 minus V upon R1. So V equal to epsilon 1 minus I1 R1. So what will be the I1? So I1 will be epsilon 1 minus V upon R1, and V equal to epsilon 2 minus I2 R2. So what is the I2 from there? Epsilon 2 minus V upon R2. Got it? So I1 and I2 came from that last two equations. Okay. So I equal to, now rearrange this thing. Okay. So I equal to epsilon 1 upon R1 plus epsilon 2 upon R2 minus V1 by R2 plus 1 by R2. Rearranging this equation will give you this. Okay. So you have to separate the numerators. So epsilon 1 upon R1 and epsilon 2 upon R2. This will separate out, and minus V upon R1 and minus V upon R2. This will separate out. So this negative sign will come out, V in bracket 1 by R1 plus 1 by R2. Okay. So put this equation as 3.51. So rearranging equation 3.51. So rearranging, and for V, rearranging the previous equation, you will get V equal to epsilon 1 R2 plus epsilon 2 R1 upon R1 plus R2 minus I R1 R2 upon R1 plus R2. Mark it as equation 3.52. The equivalent cell gives V equal to E equivalent minus I R equivalent. Okay. So this is the basic formula that we are using from the beginning. So this is V equal to E equivalent minus I R equivalent. So this term is comparing equation 3.53 with 3.52. We will get E equivalent and R equivalent. Okay. So E equivalent will be epsilon 1 R2 plus epsilon 2 R1 upon R1 plus R2. Mark it as equation 3.54. And R equivalent will be R1 R2 upon R1 plus R2. Mark it as equation 3.55. Alternatively expressed as 1 by R equivalent equal to 1 by R1 plus 1 by R2. Okay. So R equivalent from this equation will be this. If you solve this 3.56 equation and find the value of R equivalent, it will be equal to 3.55 equation. R equivalent will be equal to R1 R2 upon R1 plus R2. Okay. This is the formula for also parallel combination of resistors. Okay. Okay. So this is E equivalent upon R equivalent will be epsilon 1 upon R1 plus epsilon 2 upon R2, which is equation 3.57. For n cells in parallel, 1 by R equivalent will be equal to 1 by R1 plus so on up to 1 by Rn if there are n cells in the circuit. So equivalent resistance will be equal to this, 1 by R equivalent equal to 1 by R1 plus so on up to 1 by Rn. This is equation 3.58. And E equivalent by R equivalent for n cells will be equal to epsilon 1 upon R1 plus so on up to plus epsilon n upon Rn, which is equation 3.59. Okay, so this is the parallel combinations and series combination of the cells. Okay, so very important topic from the point of view of exams. So thank you. This is all about today's lecture. So now let's see the DPP. Okay, so this is the DPP. Okay, so you are given 10 minutes and you have to solve it. Okay, so what is the first question? What is electromotive force of a cell when no current is flowing through it? So what is the answer? You can tell me in chat. So someone said A. Okay, I am only marking the answer you are telling me in chat. Okay, so second one, in a cell with internal resistance R connected to an external resistor R, the potential difference across the terminals of the cell is? Okay, someone is saying second option. Okay, the maximum current that can be drawn from a cell with EMF E and internal resistance R occurs when? Okay, someone is saying 3. Which statement about internal resistance of cells is correct. Dry cells have lower internal resistances. Internal resistance can be neglected if E much less than IR. Internal resistance causes the terminal voltage to increase when current flows. The internal resistance varies between the different cells. Okay, someone is saying B. According to Ohm's law for cell connected to resistor R, which equation correctly relates the variable? So someone is saying B. Okay, so I have completed these 4 questions. Okay, so okay, this second question you have answered is wrong. Okay, so how many questions? 3 questions are correct, 2 questions are incorrect. Okay, I marked these answers according to your feedback. Okay, so you should solve this DPP with me also, and if you are not able to solve with me, to make sure you solve after the class. Okay, so thank you very much.